So hopefully it looks like it says it's live streaming. So let's go ahead and rock into this here. So we're gonna spend a little bit of time today talking about one-dimensional motion. But before we do that, maybe I'll show you some things you could do to practice. I just sent you a Canvas announcement that talks about why you shouldn't freak out yet and drop the course. You could go ahead and read that on your own time. But one of the things that you might want to do is you know that there's this big final exam coming that's the biggest part of your grade. You want to be honest with yourself and be like, okay, am I actually understanding what I'm supposed to understand or not? Yeah, and online is horrible because it's not conducive to having a neighbor that you study with, right? In class, normally you're working right next to somebody, and it really helps, as Beatrice just pointed out. Um, yeah, and so you could join the Discord group, and I don't have the information on that. Maybe Memo does. Memo, do you have any of that? Where'd you go, Memo? So Memo, if you know about the Discord group, are you in on that?
I do not know about no Discord.
Oh, okay. So I will try and find out about that. There's a group of students who have started an informal study group. But don't forget, Memo is a free tutor. Memo, put your
Oh yeah,
email in there. And so, right, you got a study buddy right there that is paid to help you, that's an expert. So you definitely, right? It's too late to get tutoring after you fail the quizzes. You got to get before you fail the quizzes. Yeah, no. So yeah, the positives and negatives, that's what this section's all about, details. And this is something it's good and bad about the online instruction environment, right? It's um it's very unforgiving because these problems, if you miss a minus sign, you miss the question. However, usually that's the whole point in a physics class. If you're missing the minus signs, you're not getting it. And so that's unfortunately an aspect where yeah, you're you're going to be missing some points for missed minus signs or twos. And yeah, it's frustrating. It's good and bad, right? It's less subjective grading, but it hurts when you think, gosh, I really knew what I was doing and I just forgot to write it down. But of course, as a teacher or as a computer, you have no way to know that the student actually knows when they wrote down something wrong. So that said, let me show you something here. Come on, computer. Oh, there we go. It's running a little slow there. So let me show you something here. We just finished this quiz, right? You guys just finished these, so that's done. Yay. Look at this. If you don't look at this, you're setting yourself up for failure on the final, okay? So if you go inside of here, let's do that. So we've now done 2 chapters, right? And at some point, oh my gosh, that's running slow. You can see that I have a whole bunch of practice tests with the solutions, and I give you instructions as to how you should grade yourself. So we've kind of gone through some basics. Now you're ready to start doing this stuff for real. Give yourself 80 minutes. And then I did mention this the first day of class, but a lot of you probably like, you didn't hear that. Yeah, but so this is a good thing to go over now. And I'm going to be honest with you. If you take the first practice test and fail, that's actually pretty common. What I've discovered, I had a student. Whoops, sorry, let me get memo there. So I had a student who basically every time I gave a practice test, he always failed the first practice test, got a D on the second one, a C on the third one, and then he took the fourth one and he'd get a B on that. And then when he took the real test, he got an A every time. So that's just how physics is. Practice, practice, practice. And if you practice and then grade yourself, you're going to catch those minus signs and you're going to learn to watch for them because you keep getting stung. If you're, making little mistakes here and there on every problem, that's a sign maybe you could use even more practice. And let's face it, in the online environment, you've got to probably be a better student than in the face to face for all the reasons that you guys are mentioning in the chat, where it's difficult enough already. And then you're working alone and it's lonely and depressing. And so if we could find ways to get you grouped up, and I'll try and find out about that Discord and get that to you. I'll send that in the chat. I'll see if I can figure that out soon. Okay. Probably after class, because I don't want to send emails while I'm live streaming. Right. All right. So, and what else we got? Okay. So Okay. So let's do, yeah, and speed is another thing. If you're slow, you need more practice, right? And so just being straight with you guys, right? The faster, the more you practice, the faster you get, and then you have time to check your work. Yeah, so um, that's the reality of this stuff. This is the kind of stuff where we're going to be doing physics. You can see, I was just talking with a student earlier in my last office hour, and all the stuff that we're talking about in chapter 3 that you just got a quizzed on, we were using that over and over and over again with multiple layers of complicated physics on top of that. So you really want to have this chapter 3 stuff down cold so that the math is never the issue. We're actually learning the physics. So that's what this course is about, and you'll get there by the final if you just keep practicing, right? It doesn't happen overnight. Just practice, practice, practice all semester. And if you keep doing that, all of a sudden you're going to start grinding up and it will start to improve. All right, so there's that. All right, now I want to talk about one-dimensional motion for a few minutes. We got 35 minutes. Let's talk a little bit, maybe get to one example problem. That way you could try and read over this weekend, maybe do a couple easy problems, and just get a warm, a nice head start into the next chapter. So to be clear, we're doing chapter 2 in this workbook, which is chapter 3 in the online textbook. This is the last one that'll be goofy like that. Most books actually have chapter 2 and 3 reversed and match this one. So OpenStax is one of the few that has it switched. So that's why I wrote it in this way. Anyways, who cares? So I'm going to go, what did I say? Page 21, I think. All right. So I'm going to page 21 up here, and I'm going to do a screen share just so you can read that a little better. All right. There we are. Okay, and so we start off with some definitions here. So we've got vectors, but we also have scalars. And so this is why most books tend to do things in this order, where you do the vectors first, because then this makes sense. Now, yeah, so, or sorry, yeah, anyways, let's leave that out. So here, we've got another vector, and these are called velocity versus this vector, this scalar down here, which is speed. So we're going to have these definitions are really important. We need to see that there's a difference between a thing called distance and these other two things called displacement and position. They're all related. They all have units of meters. But they're all, just because they're related doesn't mean they're the same thing. And we need to learn those distinctions. The most common thing people screw up is they think that displacement, which is a change in position, they think that's the same thing as distance, which is how far you've traveled. Sometimes that actually is true, but a lot of times that is not true. And I will go into that in just a second. Similarly, speed and velocity are not the same thing to a physics person. Velocity has a magnitude, that's your speed, and your direction. All right. And so we have to be careful. Speed is like the magnitude of your velocity. All right. And just like we just talked about in chapter 3, we have vectors. You know the difference between a magnitude, a vector, and a scalar a little bit now. It will become more clear when we finish this chapter. And then there's acceleration stuff down here. All right. So that said, let me do this. Let me give you an example of what we're trying to understand here. Where is it? Where is it? Where is it? Right here. Okay. So this is really what we're going to try and understand. Let's say I put in something here where I say x is -4, the velocity is 6, and let's say the acceleration is -2. So again, I'm punching in these numbers here. Let me see if I can make this a little bit bigger. No, it's not letting me. All right, that's fine. But so I want to point out this initial position of -4 is going to describe where the person is sitting initially. Now, I haven't hit the play button yet, but when I do, this acceleration of +6 is going to be, this person's going to move this way with a rate of 6 meters per second, okay? And then the acceleration is the rate of change in the velocity. And so actually what I could do here is show this. could show, the velocity is going to be that way. The acceleration is going to be this way. And let's see what happens when I play this. Watch what happens to these things. The guy moves to the right, moves to the right, moves to the right. He stops at x equals 5, and then he moves back, and he's going to slam into the wall there. Whoa, look at that dramatic sound effect. I don't know if you can hear that through Zoom. But so that's fine. We're going to try and model this simple thing. So again, I'm going to play this back in slow motion. The idea is we want to come up with a way to model this little dude's motion. Okay, so we want to understand all these things. Like, for example, right here at the split second he stops, you can see he stopped moving there for a split second, and you can see the velocity keeps changing, the position keeps changing, but the acceleration in this case is constant. And we can see, all right, so let's leave that at that. We're going to try and understand that problem. So let me go back to the beginning. In order to do that, we're going to use these terms that I was just showing you. All right, so if I could show you again, whoops, this one. We're going to try and use these terms in these equations that we see down here at the bottom. These are the equations that are going to be valid for constant acceleration. All right, and I was telling the other class, I like to think of this as these equations that we see right here or right here, they're the same equations. They're written in two different ways. These equations try to represent an extension of distance equals rate times time. When you were a kid, you probably used the phrase distance equals rate times time. Well, what we're going to see now is this is kind of like distance equals rate times time on steroids. This is displacement, not distance. This is velocity, which is a lot like rate. And this little piece here is time. And I'm going to write these out in just a second. And what we see is, what if your rate is changing? This piece here helps you account for a changing rate, which is a little bit, all right, like I said, it's distance equals rate times time on steroids. It's displacement is velocity times time, blah, 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 blah. All right, so I think I need to start writing some equations on the board and talking about it. But I guess before I do that, I'll open it up and see if there's any questions about that big picture. Trying to analyze the motion of things in one dimension. If we can't do that, we have no hope for 3D, right? And then we're going to try and learn these equations. All right, let's take a look at the whiteboard, and I'll show you some stuff here. All right. Okay, so I'm going to start with the biggest one right here, delta x. In physics, we're going to call this displacement. And again, if you want to follow along, or if this is all easy for you, you could keep working in the book. But for now, I'd maybe pay attention no matter how boring it is. We're on page 21. Most of you in math class have seen delta x. You know that usually means x final minus x initial. So this would be a final position, and this would be an initial position. Notice these are all vectors. And now, if we're doing motion, and like this guy was just moving left and right, I hope you agree that we could write this as delta x in the I hat equals the initial or the final in the I hat minus x initial in the I hat. The idea here again is these are vectors, so are these. And now what every physics teacher in the world does, they try to be as lazy as possible because we're already working pretty hard having to write all this stuff. So one of the things that we do as physics teachers is we immediately say, well, this cancels on everything. So I'm going to cancel these I hats and I'm going to rewrite this phrase. And this happens all the time in physics. Everybody does it. Every single book you ever read will do this for one-dimensional motion. What we see is we've taken an equation that was a vector, and now what I'm telling you is we're going to write it this way, which doesn't look like a vector equation, but I'm expecting you and every other physics student to know and I hat is implied on all terms. And so that means you know that this is a vector. Now, just to show you why this is so infuriating to students learning physics, not only is it tricky and detail oriented, now it's just straight up lying to you, right? So you look at these equations up here, notice delta x is supposed to be distance, right? However, we just talked about how we can change this x vector by writing these I hats. So we're implying there's an I hat here. So even though this looks like a distance, you're supposed to know it's a displacement because of everything I just told you, that we're assuming an I hat is implied on everything in this chapter. All right, great, more fun, right? There was something else I wanted to say about this. I don't know, but yeah, okay, so that's fine. Let's leave that at that for right now. So yeah, so generally speaking, a physicist, if they ask for distance, they're going to write the word distance in a question. If they write this in a 1D motion chapter, you could ask me during Zoom, is that supposed to be a distance or a displacement? And I'll tell you. Or you should just assume it's a displacement unless otherwise specified because of this implied I hat. So after I just told you to write it like this, now I'm telling you to write it like this. That's really insane, but that's what every teacher does. Okay.
And that's only in 1D. So once we
That's
go
in 1D,
2D,
yes.
yeah. Okay.
Yeah. So in 2D or 3D, what people will write is this delta R, where R could be delta X in the I hat plus delta Y in the J hat plus delta Z in the K hat.
Great. Okay.
Yeah. And so there we see, again, there's going to be this I hat issue, and you're still supposed to know this is a displacement. So what we're doing will match up to what you do in 3D very well.
Okay.
And I guess maybe that's the reason we do it. Is that good, Esteban?
Yeah.
Right on. Good question. All right. So I'm going to look now at the bottom of the page. So I'm looking at these equations right down in here. Okay. And I'm just going to write one of them and talk to you about what all this crap means. All right. So here's one of those equations. Now, what I just told you is what is assumed on every one of these things? An I hat. Now, where does the I hat sit? Well, it's going to be on this X for sure, because there's only one of those things here. How about over here? I guess you're supposed to know that time doesn't go to the right. So we don't think of time as being a vector. So it makes sense that the I hat is on this, similarly on this. That said, what do these terms mean? Delta X would not be distance, even though it looks kind of like it. You would know that's displacement. And I'll explain how they're different soon enough. Displacement. What is V initial X in this case? V means velocity. I means initial. And X means horizontal direction. So it's the initial velocity in the horizontal direction. And you could switch it. You could do XI or X, that doesn't matter to me. I don't care about that. Sometimes other peoples will write this as V0X. And I will do that too sometimes by accident. And if you look down here at the bottom, I tell you that. Sometimes I will write that this way. And then sometimes I'll write V final without any extra subscript. And sometimes we'll write delta X as this. So just be aware that these are all the different ways we might write things, okay? So just being clear, that's the same. And then A sub X. Acceleration, X direction. Now, do I really need all these subscripts here? No. But the next chapter, we're going to be doing 2D motion. And so when we go to 2D motion, the only difference is going to be, I'm going to write this equation one time with X everywhere, And in the second dimension, I do it again, but just put y's everywhere. And so if we learn and get used to these subscripts, it should actually be easier to pick up chapter 4. So we're going to struggle in chapter 2, chapter 4, do it all again, and it'll get a little better each time. Okay. So that's great. And then finally, T is time elapsed. Whoops. Well, you could just think of it as time, okay, for right now. So, and you may be saying elapsed since when? Since it was in the initial position or in the initial state. So this is the time after the initial clock starts running. Usually it's time after 0. All right. Yeah, and so again, just making clear, there's an I hat there, there's an I hat there, I hat there. I'm going to pause, see if there's any questions here. And you can throw them in the chat. You can ask Memo anything you want to if you don't want to ask me. I understand. Just checking. The 1/2, that's just a multiplicative factor. That comes from calculus. Good question, Adrian. I could show you that maybe in office hours if you want really quick, but for right now, just it suffices to say this comes from calculus. And then it turns out this course, we're not supposed to be doing any calculus, but I will definitely show it to you if you want to see it after class, okay? So for now, just assume, is that good enough on that for now, Adrian? Yeah, okay. Other questions, feel free at any time. I'm just going to see where I want to go next. Oh, yeah. Let's maybe look at one of these other equations that we're going to look at. So again, before I erase all this, this is essentially distance equals rate times time, but on steroids, where this is now upgraded to displacement. So you could have positive or negative, things like that. Let me show you something here. Let me show you this guy again here. Where is it? Oh, right there. Okay. So in this one, okay, we're starting at the beginning. So in this case, the initial position was right here. X initial was equal to 4.0 meters in the I hat, and that's a vector. So notice the initial position is a vector. Again, we don't always write all this. This arrow down here, this is velocity initial in the X direction, and we said that was what? Positive 6. So that's 6.0 meters per second I hat. Again, normally we don't write the arrow in the I hat. Finally, the acceleration is a negative acceleration. A sub x vector is -2 meters. And because it's a change in velocity per unit time, it's meters per second, which gives us meters per second squared. That's how those units show up. It's velocity per unit time. So it's change in velocity over change in time. More on that soon. Now, this is what I want to focus on. These two parameters that I wrote up here, the initial position and the initial velocity, those are constants. They are not changing with time. There's only one initial position. Now, what does change is the position. Listen carefully. Initial position doesn't change. Position will change. So that's why we oftentimes add the extra word. The initial position is a constant. The final position is a function of time. It changes over time. Similarly, the initial velocity is going to be a constant. It's one number that doesn't change. However, the velocity or the final velocity is a function of time, and it's going to run. So when we run this thing, let's get an idea for how much distance it travels versus displacement to talk about those words. So let me clear all these drawings. Let's run this. Started out at 4. He's going to go over here, I think, to 5. Let's speed this up. He's going to end up at -10, right? So if I could just draw that motion on my whiteboard, the idea is the guy starts right here at x initial equals -4 meters, goes over here to 5, and then comes way back here to x final equals -10 meters. So in this case, this is supposed to indicate the motion of the guy that we just watched. So I just want to point something out. You probably know this. How much distance did this dude travel? Well, what's this distance right here?
That should be 9, right?
Yeah, so that's
then
9
plus 10,
meters. Careful,
then so
what's
it's
somebody
9.
else? Esteban, that's good. I just want to get somebody else involved. Somebody else, what's this distance? If you could unmute or put it in the chat.
19 meters in total.
Oh yeah. Well, wait, what's
It's
this?
I mean 11,
15.
11 meters.
So this part is 15, right? From 5 all the way down to -10. Do you see it?
Right.
Okay, good. So then the total distance, what's the total distance? 24, right? So the total distance is 24 meters.
Okay.
What's the displacement?
6?
Nope.
No. We started
Let's
off
look
at
carefully.
-4, and then you go to -10.
It's the implied I hat. Remember, imagine there's an I hat on each one of these. Don't overthink it. If there's an I hat on each one of those things, what is x initial in this case? Give me the number.
-4.
-4, right? Okay, and there's meters. And then what's the final position?
-10.
Yeah. So -10 minus -4 equals -6.
Okay.
And
Got
so the distance is 6. But that's the distance between these 2 points. That's not the distance this person has traveled. See where I'm getting at with this being tricky? So notice the displacement. If I put in the I hats here,
It's a
delta
it's a
X.
position.
Yes, it goes 6 units to the left. So we don't usually write the I hat, but we know if it's a negative number, that implies negative I hat. That means to the left. So the person was displaced 6 units to the left. That doesn't tell the whole story. That will help us find out where the person is located. If we know they're initially located at -4 and we know their displacement is -6, we would then know the final position is -10. So that is potentially useful. But the distance traveled is much trickier. It has all this stuff in it. And so in general, this is the issue one has to look out for in a physics problem. A lot of times, things only move in one direction. When things move only to the right, or when things move only to the left, in those cases, distance and displacement are pretty much interchangeable, perhaps with an absolute value sign. But whenever something reverses direction, they're not the same thing. And that's what I wanted you to watch out for. The same idea could be true here for average velocity versus average speed. If I could, I'm going to just hold it up here because it's faster. Notice these two. Notice average velocity versus average speed. Average velocity is displacement over time, or change in position over change in time. Average speed is distance over time. Anytime distance and displacement are not the same, which means anytime something reverses direction, average speed and average velocity will not be related directly either. Ah, the joys of physics, right? Okay. So why don't we do a kind of a real physics problem, and I'll get you started on it, okay? So I'm going to go ahead and leave a good question for you to work on at home is 2.1 to lock in this new stuff. So you do 2.1 at home, all right? And now there's a strategy here that I'm going to try and follow while I'm doing this problem up here. So we're going to have to talk more about this strategy next time, but just I'm looking at the clock and we only have 10 minutes. I want to get a good start on this problem. So again, I'm going to do 2.1 point a quarter, 2.1 and a quarter, and I'm going to use this strategy to do the work. And that stuff is all on pages, basically bottom of 22, top of 23, all right? So let me get set up here, and I'll bring the question up so you could see. So again, this is the strategy I'm going to try and follow. Notice read, draw, label, list some crap. The very last thing you do is plug in numbers, okay? The very last thing you do is plug in numbers. That's a big deal in physics. And this is the problem I'm going to try and handle. So I'm going to work this out on the board. And yeah, so give me just a second. I'm going to draw it and then I'll show my whiteboard in a minute, okay? So I just got to get the work on my page here. I think if I read that right. Okay. So hopefully you've had a chance to at least read it and catch up. That's what we're going to work on right now. Okay, so notice when I'm doing my work, what am I going to do? Obviously, I'm going to label it with the number of the problem so I can find my work later. I'm going to draw the picture myself on my own paper. I read the question and I wrote down important stuff from the question, right? I'm not just leaving all the numbers on the paper. I'm getting them on my work surface. So that's a little weird these days. You might have a whiteboard, you might have a Surface Pro or something or whatever, or maybe you're just using paper, which would be normal. So, but whatever it is, I'm getting things off the book onto my work surface so I can see it without having to constantly go back and forth. And now I think I have all the key stuff there. And then these were the words that I see. Great. So I know that I'm going to try and use a kinematics problem for this. Oh, actually, let me read the question. I forgot to read the question. So is G gravity? So parts A, B, and C here are written so that I don't forget to tell you these. So these are not that big of a deal, but let's get these straight. G is not gravity. And then part B, G is not the acceleration due to gravity. G is the magnitude of the acceleration due to gravity near Earth's surface. Blah, blah, blah. It's a bunch of words. For right now, you don't really need to know that. We will get into that more later on. But so for right now, just know that G is not gravity. G is not the acceleration due to gravity. It is the magnitude of the acceleration due to gravity. It's basically just a number. If you've ever heard how many G forces do they feel, it is that G. Okay, so it relates to gravity. It relates to the acceleration. It's the magnitude of it. Also, part C, this is a pet peeve of mine. G is always positive. Always positive. It is never negative. So it is never okay to say G is negative 9.8 ever. If you don't know why I'm so picky about this, just, okay, we'll talk about it next lecture more. Let's get to this problem. Now, I have a bunch of stuff here. I want to get this into the form where I can use some kinematics equations. We were just talking, I want to analyze some kinematics problems. And I said, these are your kinematics equations. So I'm going to look and see, I see a whole bunch of symbols there. I'm going to write those down on my paper and see which of them correspond to these pictures on the board. So I'm going to say, let's do it this way for right now. You could either use x initial and x final or delta x. I know there's v initial x, the initial velocity in the x direction. These are the 5 variables that appear in those equations we were just talking about. So while this might not be obvious where they came from now, it will be soon enough. These are the 5 variables that relate to the motion of things in one dimension with constant acceleration. In this case, I don't see anything in the wording of the problem that tells me delta x. In fact, this is an unknown. There's a classic thing that physicists do. They often say this is WTF. What to find. I'm sure that's what you were thinking, but this is actually the goal of the question. If you read part D, that is what to find. So where is that one? Right? This one, part D of this question says, how far will the plane travel, blah, 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 blah. That relates to how far it's going. So this is something that relates to how far. So notice already something that students love. You're supposed to be doing, like in math class, most students are like, oh, I'm really good until it's word problems. Physics from this point for the rest of your life is all word problems. So get used to it. Yeah. My goal is to try and help you understand the words and what's that supposed to mean to you in a physics class. And that should help you figure out some of these little pieces. I'll give you an example. Okay. So how far? Now the initial velocity in the x direction, to me, that looks like this number right here, right? It's 170 miles per hour. Now, wait a minute. In physics, we almost always immediately change things to meters per second. You're going to see why. Miles are not a convenient unit for a physicist. Meters and seconds are much better. So we're going to try and convert that. Now, that's a chapter 1 task. That is, you see why we did chapter 1. Next, v final x. What do you think the final, what do you think v final x is?
Should be 0, no?
Well, why do you think that? What's the key words that made you think that?
Well, you're looking for how far the plane traveled once it finished. Basically, once the velocity went down to 0, no? I think that's...
What are the key words written on this whiteboard that tell you velocity went to 0? You're right, Esteban.
Stop.
Stop, right? So excellent. He was all over it. So that is what I'm talking about, where you're supposed to read the words, and when you see this thing stops, you're like, oh yeah, duh. If it stops at the end, the final is 0. All right. What do you think a sub x is? I'm running out of room here. Let me fix this line. A means acceleration in the x direction. What do you think that's going to be? Somebody other than Esteban, because he chimed in already, and whoever else that was that said 0, somebody else. Go ahead, take a chance. It's okay to be wrong.
0.175 G.
All right. It turns out that's not quite right. And you're right, G is 9.8. So everything you said was right so far. Something's missing. So I don't know who that was that spoke up, but I appreciate it. Thank you. Do you want to try and guess what you made a mistake on there? That's the 0.175. That's the G. That was all good.
But I'm not sure.
Okay.
Is
Anybody else
it-
can.
Is
Go
it
ahead.
because it's supposed to be minus?
Why should it be minus?
Because we're decelerating?
Slows. So see this? Oh, don't you love physics? every word in a physics problem is like a precious little jewel that you have to cradle and cuddle like a Fabergé egg. So yeah. All right. Hopefully that makes sense why it's slowing to a stop. If you're moving forwards and slowing down, acceleration is negative. Now watch out. If you're moving backwards and acceleration is negative, you're speeding up. In fact, I've written this all out for you here. It's the last piece of information on the previous page. Right? If your velocity and acceleration are the same sign, you speed up. If they have opposite signs, you're slowing down. Think about it like this. If I could go back to this moving man animation here, and I know it's time to go, so anybody that has to leave, feel free to leave. I'm going to keep going, and I'll finish this in the live stream, all right? So I'm just going to go ahead and finish this up really quick. But if I could record this, playback. Notice in this case, when the two arrows point opposite directions, where was my, oh my God. Oh, I'm not screen sharing. Sorry. My bad. And I see there's lots of questions in the chat. Memo, try to get to them as best you can. And I'll try to get there. Look, this is the velocity, positive. This is the acceleration, negative. Watch the person when I play it. Oh, and let me just get rid of those. Okay. Notice they're slowing down, and I'm going to slow down the simulation. They're slowing down, slowing down, slowing down. And now look, when the two arrows point the same way, this guy's going to be speeding up. So when you have a negative velocity and a negative acceleration, you speed up. That's what I was just trying to get at here. Now, the point being is at this point, you could take all this stuff and probably do the rest of the problem, but we're going to pick up here next time. So I'm going to go ahead and call that good. But let's see if anybody has any questions before I stop the live stream, we could do that. Yep. I see a lot of excitement out there, right? I tell you what, though, nothing is more fun than physics when you get it figured out. Nothing is more frustrating while you're trying to learn it, but it's very rewarding. I don't know, Memo, do you have any words of encouragement you could offer these students right now, please? Maybe to make them feel like I don't know, if you're willing to do camera, that would be cool too.
Words of encouragement.
Yeah.
I have none.
Anything,
No.
right? Whoops. Oh my gosh, this thing keeps beep. Was there anything that you remember from this time? Was it hard for you when you started?
Yeah, it was pretty hard. It was pretty difficult, but just staying at it, reaching out to tutors and getting help from your professors
Yep.
definitely helps. So just don't be shy to ask questions, no matter how silly you think they may seem. Just reach out to professors, tutors, and seek help. But just keep on grinding at it. It may not make sense, but you just gotta keep on going and take time to show all your work and just go slowly as you can, just so it makes sense. That's what I did.
Yep. It's also, I mean, there's math and physics being layered on top of each other here. And so there's going to be times where it's the math that's confusing you and times where it's the physics. All I could say is the more problems you do, the less times it will be the math confusing you and it will be just the physics, which that means you can be just focusing on learning the physics in the solutions rather than the math. I don't know. Would you say that's true, Memo?
Yeah, focus on that.
Yeah.
There's a lot of things, I struggle too with my math and physics classes in the beginning. I wasn't it takes a while sometimes, but you'll get there if you just keep on practicing and reaching out.
Yep. How many hours a week did you spend on physics problems back when you were doing physics 110 or 161?
I spent about 10 to 15 hours, only because I had the
A
opportunity.
week, right?
Yeah, 15
Yeah.
hours a week. And just because I had the time, and it's different for everybody, but
Especially right now, obviously. Everybody's got crazy life situations going on.
yeah, just try to make time and find a way to get it done and do as many problems as you can, because it helps. It really does.
Right on. What about the practice test? Do you think they can learn something from the practice tests?
I think they'll learn how your testing style is,
Mm-hmm.
but not necessarily like every test is different. So don't rely on practice tests, but it's good. Don't just focus on practice tests. Focus on practice tests, homework problems, and other recommended problems.
Gotcha.
Yeah, that's what I did.
Right
Yeah,
on.
don't rely on practice tests.
Gotcha. Yeah, and I mean the practice test questions are basically the same as the workbook questions too, right?
Mhm,
So that's why I did it, right? It's basically
Yeah.
all the test questions that stumped my previous students are now in the workbook. So they're just tricky questions filled with, this is a whole book filled of my test questions. So as far as my class goes, you'll learn the wording really well, right? So
Yeah, it's just the test, when you take a test, you feel this pressure and you feel this stress, and that's why doing as many problems as you can helps you to take away that stress to, get comfortable. And
yeah, gets your
Yeah.
speed up and it reduces your probability of making typos basically.
yeah,
But
oh yeah,
you're always going to make typos, right? You
always,
just,
yeah.
I mean, you could see it. I've been doing this for years. I wrote thousands of problems and I still make typos. So, all right, I definitely am going to stop
Yeah,
the live
it
stream.
happens.